Hi guys, can you hear me?
Yeah, yeah.
Anyone can hear me? Volume. I think my mic is okay. Uh, is my volume low or something?
Is it fine? I think so.
Okay, I'll send the question. Should be a short statement. I sent it in the chat. Take 1 minute and read it. Okay. So let's read the problem. So we are given an array of n integers, and your task is to process q queries of the form what is the sum of values in range AB. So we're given nq and n integers for the array, and for each query we are given two integers a and b, and this represents the interval that we should print the sum of it. So we should print the sum of values between a and b in the array. Okay, so let's see an example here. So here is n, the size of the array, and q, the number of queries we are asked, and here the elements of the array. So for the first query, where we are to print the sum from 2 to 4. So from the second element to the fourth element in the array. And this should be 11, right? And for the second query, we should print the sum of the elements between the fifth and the sixth element. So here's the fifth and sixth. So this should be 2. And here 1, 8. So the sum of all the elements. I won't calculate this sum. So it would be 24. And here I'm given 3 and 3. So I want to calculate the sum of elements between 3 and 3. So it's just one element, which is at index 3, which is 4. Okay, that's right. So this task should be easy and doable. So I want your suggestions. Can anyone tell me how to solve this problem? Anyone?
We can use a pre-sum array.
Is anyone talking? Your volume is your sound is too low. Can you raise it?
We can use a pre-sum.
Let me test my audio very quick. Sorry. Mm. Okay, so my audio, the sound is working very well on my side. So can you talk again? The
Can you
person.
hear me?
Yes, yes,
Is it
that's good.
audible?
Yes, yes, yes. I can hear you good.
Okay, so I was saying we can use a, yeah, we can use a pre-sum array. This.
Prefix sum array. Yes, good. So that's exactly the answer to this question. So for those of you who don't know what a prefix sum array is, so it is just if you want, if we have some array called prefix or pre, and it is of size n, and pre of I equals to the sum of elements from the start to ith element. So this is what's meant by prefix sum array. So the prefix sum at any point equals to the sum of elements from the start of the array to the ith element. So whenever we want to get the sum of any subarray, let's say here 5111, 511, so the answer should be prefix at this point, at I here, minus prefix of this point. So it will just get us this subarray, right? So let's calculate this very quickly. First, we'll take NQ, then the array itself. And the values could be up to 10 power 9. And the number of integers are up to 2 times 10 power 5. So the prefix sum array should be long. So here I took the array from the input, and I want to calculate the prefix sum. So the prefix of the prefix sum of the first element is just the first element. So pre of 0 equals to a of 0. And then we'll go starting from 1 until n and calculate the value for each I. So pre of I should be equals to a of I plus pre of I minus 1, right? So the prefix of I should be equal to the prefix of I minus 1 plus the ith element. And here how we calculated the prefix sum for each element, for each position. Okay. And then I'll process Q queries and then take A and B. But here A and B are given one based index and we are using zero based indices. So I'll just decrease A by 1 and B by 1 to be zero based indices, okay? And then I'll just print here pre of B minus pre of A minus 1, right? So the sum of elements between A and B is the prefix of B minus the prefix of the position before A, right? But there is a problem. So if A equals to 0 and B equals to 5, then I'm here calling pre of A minus 1, which is negative 1, and this will give us segmentation fault. It's out of bounds. So I should fix that. So I should call pre of A minus 1 only if A is greater than 0, right? So I'll just make something here, some small condition here. So we have here in C++ to make if conditions, we can make this condition and question mark, and here what happens if true, what happens if false. Okay, so here we can write in one line if we want to make something very quick but with a condition. So we can make this is like if. So we write here a condition and then after it question mark, and then if it's true, then what is here will happen, and if it's false, then what is here will happen. Okay, so we can put it here. So pre of B minus A greater than 0, then so if A is greater than 0, then I'll just subtract pre of A minus 1, right? Else I'll just do nothing. I'll subtract 0. Okay, is it clear here? That's it. So let's test it.
So Ahmed, the else condition, is that correct? The else condition.
Yeah.
Colon 0 that you said. Should it be colon 0 or pre-A? Pre-A.
Should it be what, sorry?
Should it be 0? Should it be just 0 or should it be pre-A?
No, 0, because if A equals to 0 exactly, then if I subtracted pre of A, I'll subtract the element at the position A, but I want it. So let's say here B equals to 5, A equals to 0. Then I want the sum of all elements from 5 to 0. But if I subtracted pre of A, then I'll just get the sum of elements from 2 to 4, from 2 to 5. Right? Did you get that?
So it should be pre-A, right? I mean, pre-0, right? No?
No. Look, so whenever I'm given an interval, so I should print pre of right minus pre of L minus 1. Why minus 1? Because I want the value at position L. So I'm subtracting the pre of L minus 1. But if A equals to 0, then I should subtract the value of pre of 0 minus 1, which is negative 1. And there is no element like that. So I'll just subtract 0.
Okay.
Okay, did you get it?
Yeah.
Okay. If something is not clear, make sure you ask it again. Okay, no problem. So here we tested and it gives correct output. Let's erase this. Okay, let's submit. And let's test first the part that we are given A of 0 to make this clear. Okay. So it's any array of size 5, and here one query, 1, 2, 3, 4, 5. And here query would be between 0 and 3. So it will be the first 4 elements, right? So it should print 10. 4 plus 3 plus 2 plus 1, this is 10. So it's good that we tested that here. Oh yeah. So here, yeah, from 0 to 3, I shouldn't print that. So A and B are given between 1 and n. So I shouldn't put 0. I should print 1. And here it is converted to 0. So I put 1 and 4. So the first 4 elements, right? So it should print 10. And it printed 10. So it printed 3 of 3, which is here, minus 0, which is 10. Let's submit. Okay. Okay, let's see the second problem here. Actually, it's the same thing, but with a small modification. I sent it on the chat here. Okay. So again, I'm given an array of integers, and I'll have to process Q queries, and I'll have two types of queries. Okay. So for the second type, I should print the values in the sum of the values in the range A and B. But the first type of the queries is I should update the value at position K to U. So for example, let's take this example here. So I have two types of queries. Query of type 2, which is presented by 2 at the first. Right? Is that right? Yes. So query of type 2, which is presented by 2, and query of type 1, which is presented by 1. So query of type 2, we should print the sum of the values between A and B, like the last time. Okay. So here we'll print the sum of the values between 1 and 4, and here between 5 and 6. But here, query of type 1, we should update the value at the kth position to U. So we should update the value at the third position to 1. So let's look here at the array. The third position is 4. We should update it to 1. So at this query, we will not print anything. We'll just update the value. Okay. And after it, when we are asked about a query of type 2, we should print the sum of the interval in the updated array, right? So here 1 and 4. So note that at the first query, I'm asked between the sum of 1 and 4, and at the last query, I'm asked again at the sum between 1 and 4. But here, the third element is changed, so it will change the sum, right? So here the first, this 14, 11. So here the answer is 14, and here the answer is 11. Because that was 4 at the beginning, and at the end it was 1. So the value decreased by 3, the difference between 4 and 1, right? So here's the problem. Tell me if you have any ideas how to solve this. How can you modify our solution to make this work?
Like using the same pre-sum array would increase the time complexity.
Yes.
Yeah. So I think will segment tree help?
You think what? Sorry?
Segment trees.
Segment tree, right? Yeah, that's good. So very good. We should use segment tree. So I want to make sure how many of you doesn't know or know segment tree. So can you? I'll explain it anyway, but can you tell me, all of you, do you know segment tree or not?
No, we don't know.
No.
Okay.
Don't know actually.
Hmm? Okay, so I'll explain what segment tree is. So it is some data structure. So let's first see the naive approach of how to solve this using the easiest way. So of course, to solve this using the way of the solution of the first problem, we will just update the value of this array. We'll just set it to 1. So we'll just say a of 3 equals to 1. That's it. And then we will pre-calculate, we will recalculate the prefix sum array again. Okay, so we'll just, every query of type 1, we will calculate the values of all the prefix sum arrays again, right? Because if we changed this value, so it actually changed the values of all the prefix sums of the elements after it, right? So prefix of here is changed, prefix here change, and so on. So the total time complexity of this solution, if we have 10 power 5 queries, 2 times 10 power 5 queries, and at each query we will spend, if we have 10 power 5 queries of type 1, and at each query we'll spend O of n complexity to update the prefix sum array. So the total complexity would be O of n squared, right? But this is so bad. So we want to make at least something like O of n log n, or O of n square root n, or O of n. Okay.
And can we also go with the same approach of
Can we what?
using the prefix sum?
So you want to see it? How does it work?
No, the thing is, what I'm saying is we will using, let's say, before the 1 comes, with the type 1 comes with 3 and 1, we will be using the same prefix array to calculate the sum, right? Like for the first example, 214, the sum is 14, right?
Yes.
And in the last 214, the sum is 11. The difference came because the third element has been changed to 1. Now we will store this difference somewhere, that at this index the value has been decreased or increased. Now if the range 1 and 4 purchase that particular index, then we will subtract that much amount only. So we won't change the prefix array of ours. We'll just change the whatever one type of values has been decreased or increased by.
Okay, yeah, I got you. The thing is, this approach wouldn't work for many queries. Why? Because if we have too many changes here, and then we are asked about too many sums here, right? So here I change the first element, for example, and here the second element, and here the third element, and so on. So I'll end up having too many elements that want to be changed, right? So here at the
So
first, yes,
so I was saying that we'll just the number of differences would be number of elements itself, right? Maximum.
the
So
number of
we'll
difference
just
would be what? I didn't get
the
you.
type 1, the number of type 1s can be the number of elements itself, the differences, because we'll always store the latest difference.
Yes,
It
but
is
I mean we changed too many indices. So we changed this
okay.
index and then this index and so on. So then I'm asked. So let's forget about the actual queries here. Let's explain about the on the array itself. So here I'm asked to change this element to something, this element to another thing, and so on. Okay, and then I'm asked to calculate the sum from here to here, for example. So what you're saying is I should check about only the the positions that were changed and then know what's the difference. But here I know that there are many positions that are changed. So how could you deal with that? So I'll change like 4 or 5 positions in this particular query, right? So I know that this element is changed and this changed, this changed, and this changed. So if I want to calculate the sum of this subarray, I'll have to look in that somewhere about on these
For
5
each and
changes,
every element.
yes, and calculate the differences.
Yes. So
So
that would give the same complexity of n square.
yes, so this should be of n squared also.
Yes.
Okay,
Okay. Got it.
so let's see what the segment tree is. So segment tree is a powerful data structure that calculates many things in log n time only. Log n. So let's draw. Okay, so let's say we have an array of exactly 8 elements. So here's our array here. Okay, and the positions are 1, 2, 3, 4, and so on. And I want to ask about the sum. Let's forget about update now. So I want to ask about the sum of values between the third element and the seventh element. Yeah, so yes, the third element and the seventh element. So what segment tree allows us to do, so we know that with prefix sums, we could calculate this value in O of 1, right? So prefix here minus prefix here could be calculated in O of 1. But in segment tree, I can calculate this value in O of log n. No, this is slower, but segment tree have updates. So I can update any value, like I'll say later, in O of log n. So here I want to find this sum in exactly log n operations using this segment tree. How this could done? So this is done by pre-calculating the segment tree as follows. So a segment tree is just a tree that contains nodes, and each node is connected to 2 nodes below it. So here it is connected by here, here, here. So this is, it's clear that this is a tree. And the leaf nodes here represents the actual values of the array. Okay, so here 8, 9, 10, 11, 12, 13, 14, 15, these nodes represents the actual values of the corresponding elements in the array. Okay. Okay, so the upper node for each two nodes, so the parent node, let's call this the parent node. So 7 will have the value of 14 plus 15, not 14 plus 15, the value in the node 14 plus the value in node 15. And here 6 will have the value, the sum of node 12 plus 13, and so on, until 1 contains sum of all elements. So at node 1, we have the sum of all elements of the array. And at node 2, we have the sum of elements in the left half of the array. Node 3, we have the sum of elements in the right half of the array, and so on. So whenever we want to calculate the sum of any interval like this, let's see how this is done with segment tree. Let's look at the first node and have some interval around it. So let's look at the first node, and here this is our looking area. Okay, and then we will find that this node is not entirely in our interval, right? So we cannot get something from here. So we'll just go to the next two child nodes. Okay, and then see, is this node entirely in our interval? No, it has left part and right part. So its right part in our interval and its left part is not in our interval. Okay, so we'll just go to the child nodes here. And what we'll realize here, that this node is entirely out of our interval, right? So this represents the sum of the first two elements. So we'll just not consider that. So we'll just return 0 here. And we'll not continue with the segment tree here at this left part, okay? And at this part, at node 5, we'll find that it's completely in our interval, right? So it represents the third element and the fourth element. So we'll just return it. So we'll somehow have the value of it and get it with our sum that we are calculating. Okay. So here we are standing at node 3, and we'll find that its left part is in the interval and its right part is not. So we'll just go to the next two childs. And here we'll find that node 6 is completely in our interval, right? So we'll just return it. So we'll have the value of it. So now we have the value of 5, 6. But 7 is still not completely in our interval. So we'll go to the next two childs. And here we'll find that 14 is completely in our interval. Actually, it's the rightmost element in our interval, and we return it. So that's it. So here, instead of calculating the sums of these 5 elements, we calculated the sum of the nodes 5, 6, and 14. That's it. So 5, 6, and 14. Did you get that? Did you get the idea, the core idea?
Yes, Amit.
Okay. So this is what segment tree is. And the time complexity for this lookup is log n, because at any size of interval we are given, so at any size of any interval, we will, at maximum, at most, we will get the values of log n nodes, right? Because if we have x, for example, so if the interval of size x, let's make text. So if we have an interval of size x, okay, we are looking at an interval of size x. So at least we will have the value of some node of size x over 2 in our answer, right? So if x is 9, for example, so I find that I'll get the value of a node of size at least x over 2 in our segment tree. So let's take this example here. So this interval is of size 5. Let me make this close enough. Okay. So our interval here is size 5, 1, 2, 3, 4, 5. And I'm claiming that at least one element of size 5 over 2, one node of size 5 over 2 will be in the segment tree, and we'll get the value of it. And we can see why this is true here. So node 5 is of size 2, so it has 2 elements, and 2 is 5 over 2 actually. And node 6 is of size 2, and 2 is 5 over 2. So whatever x is, we will have some node of size x over 2 in our segment tree, and it will be calculated. Okay. So this is the idea behind segment tree. Let's see how could we calculate it. So we will do this using top-down approach. So we write a recursive function to calculate the values of these nodes. So we said that at first we have the elements of the array stored in the last nodes here, right? And then for this node, the value of it will be the sum of its two childs. And for this node, the sum of its two childs. So we'll make a recursive function that starts from the top at this node, and then calculate its sum from its two childs. So the sum of node 1 will be equal to node 2 plus node 3, and node 2 will be 4 plus 5, until we reach to some leaf nodes here in the tree, and return the values of it. Okay. Let's make the function for calculating segment tree. Let's set the size. Let's have our array, our original array. And so let's see what's the size of the segment tree. So can anyone tell me what's the number of nodes in segment tree? So if I have an array of n elements, so what should be the number of nodes in the segment tree? Should it be n log n, what? So I have here 8 elements, and the number of nodes here, let us calculate that.
2 to the power n minus 1?
What do you say again?
2 to the power n minus 1?
2 to the power n minus 1? Oh, that's very large. No. So 2 to the power n, this value is extremely large. So if n is 10 power 5, so 2 to the power 10 power 5 would be an unusable number, which has too many digits. No, this is too far, sorry. But you are close. Did you mean 2n or 2 power n? Okay, so actually let's say so it's 2n. Why?
Oh yeah.
So it has proof on the internet, but let's not dive on the proof. But you will see here why it's 2n, because at the lowest nodes we have n. So at the lowest nodes in the tree we have n nodes, right? So for the parents we have n over 2 nodes, right? So here 8 and here 4, and then we have n over 4 nodes, and then n over 8 nodes, and so on until infinite, until 0, until 0. So actually this should be until 1, right? But let's say this is an infinite sequence. So this sequence should be equals to exactly to n. Okay, so whatever n is, and until infinity or until 0, this should be exactly to n. Okay, there are multiple proofs on the internet, but one proof I like it is through geometric looking. So if you consider um, a square of size n, for example, or some segment of size n, and let's elaborate that. If you consider some segment of size n and another segment of size n over 2, and exactly n over 2, another segment of size n over 4, and then n over 8, and so on, the sum of all of this should be exactly to n. But why? Let's see it another way. So here we have n over 2. Let's not add the n over 4 here, but let's add it here. And then we'll have n over 8. And then we'll have n over 16. And then we'll have... So each time I am just drawing a segment that's half the segment before it. So this would converge to 2n, and it will never pass the first segment of size n. So it will never pass it. So I'll just have to always decrease the size of the segment by half, by half, by half. Okay, so this should be exactly 2n.
Or else we can say that the summation of infinite GP is a upon 1 minus r. So a is n, r is 1 by 2, so it will be 2n like that.
Sorry, I didn't get you very good. So
Like summation of infinite GP is a upon 1 minus r.
a of what?
A divided by 1 minus r.
A divided by 1 minus r. I cannot understand that.
So a will be the initial value. R is the ratio of previous to the previous to n to n minus 1 ratio. Like so, it will be a will be n and r will be 1 by 2. So it will be 2n.
Oh, so you are saying about the proof of this, right?
Yeah.
Oh, yeah. Okay, good, very good. So I was speaking that this geometric proof is very good, actually. I loved it. Okay, so let's calculate the segment tree. So now we know that the size of segment tree is 2 multiplied by m, right? But actually this doesn't work here. So we have exactly 2n, not exactly, so it's 2n minus 1 elements or so. But we shouldn't set the size of exactly 2m. But why? That's because if we are at some node, so let's see how. Let's make this open and see how to store the values of node, and now we'll see why the size is actually greater than 2 times n. But we know that we have exactly 2n nodes, or around 2n nodes, and the first node is called 1. But here we have 0 position indices, so let's say segment of 0 have the first element. Okay, so the second element should be at index. So let's look at this one. So the first child at 2 and the second child at 3. So by looking at this, you will find that the first child, the position of it is the position of the parent multiplied by 2, right? 1 times 2 is the position of the first child. And the second child is the position of the parent multiplied by 2 plus 1. So here 3 equals 1 times 2 plus 1. Let's look for 4. So 4 equals 2 times 2. 5 equals 2 times 2 plus 1. 6, 3 times 2. 7, 3 times 2 plus 1. And so on. Let's look at 12 here. 6 times 2, 13. 6 times 2 plus 1. So for this pattern, the positions of the childs, we know that it's parent times 2 and parent times 2 plus 1. But since we are zero-based indices, so we'll have the first node at 0, and the first child at 1, the second child at 2. So following the same pattern will not work here. So 0 times 2 is not 1, and 0 times 2 plus 1 is not 2, but instead it's parent times 2 plus 1 and parent times 2 plus 2. That's it. So 0 times 2 plus 1 is 1, and 0 times 2 plus 1 plus 2 is 2. Let's look at another. So for this child, which is 1, let's see what are the childs of this one. So the child should be 1 times 2 plus 1, which is 3, and 1 times 2 plus 2, which is 4. And if we drew that, we found that this is right. So here, let's say this is 0, 1, 2, and for this one, we have 3 here, 4 here, 5 here, and so on. So 3 is 1 times 2 plus 1, 4 is 1 times 2 plus 2, and so on. Okay. So let's calculate the values of the segment tree now. Let's make a function called build. And build takes 3 parameters.
Hi, Ahmed. One question I have before you move on. So, like prefix sum array and suffix sum array, I was able to understand how we are basically maintaining the sum in the prefix and the suffix array. However, in segment tree, I don't understand the logic how we are maintaining the sum of the nodes or basically any operation of the nodes. Can you help me with the logic here?
Okay, no problem. So before going into the logic, you should clearly understand how we build the segment tree. So do you understand clearly how the segment tree is built, or what is the construction of the segment tree? So what each node represents? Do you understand now that each node represents the sum of the 2 child nodes?
Not really.
Okay, so first let's say what a segment tree is. So let's say segment tree, it's just a some random tree that doesn't represent any sum or anything, and we'll just store values in it. Okay, so it's clear that here this is tree, so it's some graph that doesn't have any cycles. Let's remove this. Okay, let's leave these lines. Okay, so it's just some random graph, and this graph is tree because we don't have any cycles. So it's just tree with some nodes. Okay, so at first, to construct this tree and to see what is the meaning of the segment tree, we will put at exactly n nodes. So we have an array of size n, so we'll have n nodes that have exactly the same elements in the array. Okay, so we have here the array of size 8, and we have here 8 nodes that have exactly the values corresponding to it in the array. Okay, but to make this more helpful, we will add some parents to conclude the sum of the 2 childs for it. So for each 2 nodes here, we'll have some parent which have the value of the sum of these 2 nodes. Okay, so let's say we have here 1 and 2. So here this parent will contain 3. Let's say here we have 5 and 6. So this parent will contain 11. Okay, so let's say we have here 1, 1. This will contain 2. And 0, 1. This will contain 1. Okay, and let's continue. So here we have 3 and 11 for 4 or 5, So the parent node should contain 14. And here we have 2 and 1. So that parent node should contain 3. And here for the last node, the big parent should contain 14 plus, what is this? 3. So 14 plus 3, which is 17. 17. Okay. So this is a segment tree. So a segment tree is some sort of tree that have some nodes, and each node contains the value of the contains some information about its child. Okay, so it's a tree such that each node contains some information about its two childs. But in our case here, we have each node contains the sum of our two childs. That's it. So can you tell me what's your problem exactly in understanding the construction of the segment tree? Did you get that? What's meant by segment tree?
Yes, this part I understood. So, just one small question. So, while constructing the tree, do we have uh, all the elements from the array as leaf nodes?
Yes, yes. So that's what we're going to see now, how we could build that. And actually the building is so easier than you think. It's just a recursive function that will calculate everything. Right?
Okay.
Okay, so let's see how we could build it. Just build the array. So here we will have 3 parameters in the build function. The first parameter is corresponding to the left right of the interval we are standing at, and the right part, and the index of the nodes. So first we'll start at index 0. And the left part is 0, and the right part is n minus 1, right? So so for this function to work, to build the entire segment tree, after we finish this function, we should call build 0 n minus 1 0, and this should build the entire segment tree. So it will start at element 0 from the segment and contain the interval from 0 to n minus 1. And each time we will divide this interval by 2 and go to the left part and go to the right part and build them and so on. Okay, so you'll see that it's easy actually here. So let's see what's the base case here. So the base case is when we reach an interval of size 1. So here we will call 0 and n minus 1, and it will divide this interval into 2, and we'll call 0 and n over 2, and n over 2 plus 1, and n minus 1, and so on, until we reach to this node, for example. And then I'll have no more childs. So for this node, which is of size 1, I'll have no more childs. Then I'll just return the value of it. So the base case is if L equals to R, then we are at a node of size 1. We have only one element. Then I'll just return, so A should be an array also. So I'll just return A of L position or R position. So this should be L or R, because L and R represents the intervals in the actual array, not the segment tree. So L and R represents an interval in the actual array. So whenever L equals to R, then we are at some position in the array, which is, for example, if we are here at this node number 12, L will be equals to R, and this should be equals to 4. So it will be index 4 here, right? 0, 1, 2, 3, 4. So we'll just return A of L or A of right. It's the same thing, okay? So now this is the base case. So how to calculate the childs? We'll just go recursively between every childs. So we'll make an integer called middle to split the interval. So middle will be equals to L plus R over 2. So this is the half of the interval. And then we'll just, so let's not return here. So I said here that we have I corresponds to the index of the node in the segment tree, and I starts with 0, at the first node, and then we are calculating it on the go. I'll show you how. But here I have I corresponds to the index on the segment tree that I'll store in it the value of this interval. Okay, so segment of I here should be equals to of L. Okay, and I'm done with calculating the value of sig of I, I'll just return sig of I here. Okay, so after returning sig of I at the end I should have here returned sig of 0, which is the value of the sum between 0 and n minus 1. Anyways, let's continue. So else if L is not equals to R, then I am at a greater interval, an interval of size greater than 1. So I'll just split it into half. So int middle equals to L plus R over 2. And so the value of sig of I, so the value of this node should be the value of should be the sum of the two child nodes, right? So sig of I should be equals to build of the left part and build of the right part, because build returns an integer, and it returns the value of the sum of this interval. Okay, so this should be build of L of mid, and for the left child, the I for it, as you said, the I for the left child should be I times 2 plus 1. That's it. And for the right child, we should go to mid plus 1 and then R. So here our end is at mid, and our start for the right node is mid plus 1, and the end is right, and the index of it is I times 2 plus 2. So that's it. So that's how we calculate, how we build the segment tree. So it's a recursive function. When it reaches a node that have an interval of size 1, it just sets the value of it to the corresponding element in the array. And whenever we are at an interval of size greater than 1, we'll split it into two halves, and then go get the value of the left half and get the value of the right half after building them, of course, and then store it in sig of I, and then return segment of I. That's it. If you have any questions in this build function, just ask it now. So any questions here in this function? Anything you don't understand? Okay, no questions. So I believe everything is clear.
So Ahmad, we are going with 2m plus 1 segment tree size, right?
Sorry, what do you say again?
So 2m plus 1, the size of the segment tree would be, right?
Not quite. So the size of segment tree should be 4 times m. And this is because so many people talked about this on the internet, and there are many conversations about this. But 4m is the safe size. Why? Because if we are at the last node, so if we are at some node here, did you say any question? Okay, so if we are at some node,
Okay.
at some last node in the segment tree, and we want to get the value of we want to get the index of the next node, so it will be I times 2 plus 1 and I times 2 plus 2. So it actually turns out that for some parts, the last element of any node, so let me clear it, I don't know how to say it. So for some part, we will actually face a problem that we are at an index of size 2m or 2m minus 1 or so on. So we are at some last nodes, and then we are calling I times 2 plus 1, which is something closer to 4 times m. So I said that the total number of nodes is around exactly 2m or 2m minus 1, not more than that, right? But the actual indices we are consuming are not all close to each other. So we are not consuming 0, 1, 2, 3, 4, 5, 6 until exactly 2 times m minus 1. We are not consuming these indices beside each other. So what eventually happens here after calculating this is that our first values are beside each other, yes, but here after 2m minus, for example, 2m minus x, so this is some smaller value, we are just calling 2m minus x times 2 and 2 and 2m minus x times 2 plus 2 is plus 1. So it will eventually happen that we are calling some greater index that have passed 2n and passed 3m. Okay, but then we will have some empty elements here. Did you get that? Or it's not clear?
Yeah, I got it. So
Okay.
leaves, actually, whatever number of leaves are there, we are actually making it twice, and based on that, we are calculating the size of the segment tree. So leaves in this case, if it m, then we are assuming the leaf could go to m, and that is how we are saying the segment tree size would be 2 multiplied by 2m multiplied by m would be 4m.
Yes, exactly. Yes. Okay, so here the size of segment tree is 4m and the size of the array should be exactly m. So this is how we build the segment tree. Oh, yes, say. Do you have question?
Point. So here, hello, Ahmed, can you hear me?
Yes, but increase your volume a bit.
I'm in the maximum volume.
Okay, that's good.
Okay, so I'm in the maximum volume. Yeah. My doubt was, yeah, since as you explained, there are some of the empty array places, so that's why it builds up to 4 times that, right?
Yes.
So here, instead of using a array, why can't we use a linked list such that we can save that space?
Linked list. Why make it that complicated? So segment tree. So first, we cannot use linked
No,
list
because
because we
here,
cannot.
yeah, we are using.
Yes. Say yes.
Yeah. So.
What were you saying? I'm hearing too.
Since
Oh, actually, there is a delay on your side, I think. So go ahead and say it one time.
the
I didn't hear a word. I think your internet connection is not stable.
you, the main place is here.
Can anybody hear? I cannot hear anything. The internet connection is not.
Your voice is breaking, I think.
Okay, maybe.
Okay, my internet should be okay. So check your internet because I cannot hear you. Sorry. Okay. Okay. You might try. If you have questions, just ask it one time because your internet is not stable, so I cannot hear you. Okay. Okay, let's continue. So here, after we built the segment tree, we want to query it. So we want to make queries to check. We want to make queries to get the sum of any interval. And how we said we should do that. So we will also, like we said earlier, we will start from the first node. We'll make again a recursive function. We'll start from the first node, and then we'll check for two cases. If our current node is out of the interval, we'll just return 0, so nothing. And if our current node is in the interval, we'll... Sorry, the train is coming. Okay, that should be okay. So if our current node is out of the interval, then I'll return 0. If it's in the interval, I'll return it. And if it's not, so if it's not completely out of the interval and not completely in the interval, then I'll just return the sum of the... So then I'll just go with my function, go with the next child. So for this example, the first node is not in the... is neither out of the interval nor in the interval. So I'll just go to the childs and continue and look for each child. It's not out of the interval or completely in the interval. Then I'll go to the next child. And then I found that 5 is completely in the interval. Then I'll return the value of 5. And here 3 will return the value of 6, and 7 will return the value of 14. And our function should return the value of 5 plus 6 plus 14. So the values of... so the sum of values of nodes 5 plus 6 plus 14. That's it. So let's make a function here that calculates that. Int query, for example. And here it will take more parameters. So it will take 2 intervals. So it will take the interval of our node that we are currently standing at, and the interval of the interval we are looking at. So let's say L and R is our interval. We want its sum, okay? Our original interval. And L capital, R capital corresponds to the interval of the ith node in the sigma tree. So correspond to the interval of the ith node in the sigma tree. So these 3 parameters are about the sigma tree, and these 2 parameters are about the original interval we want its sum, okay? So let's see what are the cases. So the first case is the current interval we are looking at and the current interval in the sigma tree are completely disjoint. So they are not connected. The one is completely out of the other. So at this case, I'll return 0. So if L is greater than R, so if the left part of our original interval is greater than the right part of the current node, then of course this is disjoint. These are disjoint. Or R is smaller than L. And the same thing, if R is smaller than... if the right part is smaller than the left part, then they are not connected by any means. Then I'll return 0. That's it. But what if the current node is completely in my interval? Then I'll just return the value of the ith node. Okay. So if L is greater than equals L and R is smaller than or equals to R, then I'll return the value of the current node. So if it's not those 2 cases, then we are at some node like this, for example, where it have its left part, or it have some part in the interval and another part is not in the interval, right? So I'll just return the summation of the queries at the next 2 childs. That's it. So I'll just return summation of queries at the next 2 childs. So I'll pass L and R as they are, because I'm looking at them. First, I'll make an integer middle. And here I'll pass L and yes, and mid. So L and mid, the left part, and the index of the left part should be I times 2 plus 1. And here plus query of the right part. Query of L R middle plus 1 R here I times 2 plus 2. Okay, so that's it. That is the query function. So it has three cases. If the node is out of the interval, I'm returning 0. If it's in the interval, I'm returning segment of I. And if it's not this or this, then I'm returning the values of the next of the queries of our child. That's it. Okay. Do you have any question in this query function? Again, if you have questions, ask it now.
So in case of update, we'll just update the value and follow the bottom-up approach to update all the parents, right?
No, in case of update, we'll do something else. In case of update, we'll do another function. But here I'm speaking about the query without any update. So here, query in log n just gets the value of some interval. Okay.
Okay.
Okay. So in case of updates, we'll do something else. So here we have built the segment tree, and here we have some function that get us the sum of some interval. Okay. But what if we updated some value?
Hi, Ahmad, can you explain me that partially when it's partially overlapped, what is the logic?
Can I explain what? Sorry.
In the query.
The query function. Okay.
Yeah, the line number 24.
Okay. So here I'm saying that I know that query of so some query will return the value of some node. Okay. So query of the left part will return some value corresponding to the left part, and query of the right part will return some value corresponding to the right part, right? Because here at the base cases, I'm just returning either 0 or segment of I, whether I am at a segment completely in our interval or not. So I just to calculate the value of my current of the value I'm standing at. So here, if I'm standing at a part that's not completely in or not completely out, then I'm just getting the value of the left part plus the value of the right part. And for the left part, it is actually going to decrease the size of the node by half. So it will eventually end up being either in the interval or out of the interval, and just it will again it will eventually return either 0 or segment of I. So I'm just
Okay, we'll basically reduce the third case to again first and second case.
Yes, that's it. Okay. And here, okay, that's it. So for the update, so we said now that we have query that just get us the sum of some interval. But what if we updated? So if we updated this element, for example, so there are many nodes that should be updated in the segment tree. What are those nodes? So this node should be updated, right? And when this node is updated, then of course this node is updated because this contains the sum of 10 plus 11. And when node 5 is updated, then node 2 should be updated also because it contains 4 plus 5. And when node 2 is updated, then node 1 is updated. So node 1 is always updated because when you update any value in the array, of course, the sum of the array changes, right? So if you look at any update, we found that it will update the nodes starting from this thief node until the end, until the first node. Okay. So if we update it at node 15, then it will go like this. If we update it at node 5, then it will go like this. How could we make a function doing that? Again, we'll do a recursive function in the same manner to update any value. So when you update a value, we'll just call. So if, for example, I want to update a of 0, a of 5, then I'll just set a of 5 equals to 6. So this is an update. So I'll update the array immediately, and then I call some function and call the update. And this function will update the segment tree, but considering only the nodes that are up to 5, right? So when I want to update, for example, this element, so I'll just go immediately update this element in the array and call an update function, and it will go again from top to bottom, and then we'll see here if my index here. So we check this index that I updated, it's on the left part or the right part, and it will find that it's on the right part. Then it will forget about the left part and go to the right part and update it. And how it is updated how it is updating it. So it is getting the value of it from the sum of the right node plus the sum of the left node, but after updating it, right? So it will be updating in 6, and then 6 will find that um, this element is at its left part. So it will be updated by the sum of the right node plus the left node, but after updating that left node. Okay, so that's it. Let's do the update function. Let's make it void. We can make it void or integer. We can make it integer if we want. Let's do it void. It's better. Okay. So it will have parameters corresponding to, these are the interval of our segment in the tree, and this is the index of the node, and then here we have k, and k corresponds to the element, to the index of the element we updated. Okay, so the index of the element we updated in the array. So let's go to the last step. Let's forget about the first steps and go to the last step. So let's see. Okay, let's calculate the base cases first, like we made at query. So we know that this, so we are not going to call any update function unless this k is in this interval. Okay, so I know that k is in the interval of L and R. So I know that k is greater than or equals R and smaller than or equals to R, right? So if I reach a point where L equals to R, so I'll eventually reach a point where the size of the segment is 1. So I'll just set segment of I to A of k. Yes. So if I reached a point where I am at an interval of size 1, then I'll just set segment of I to A of k. Else, if it's greater than that, then I want to check which halves should I go to. So the left part or the right part. So I'll make middle equals L plus R over 2. And then check if k is more than or equals to middle, then k is on the left part, surely, right? Then I'll just go and update L middle I times 2 plus 1. And else, if k is greater than middle, then it is on the right part. Then I'll go to update middle plus 1 R times 2 plus 2. So I'll update the right part. Okay, and after updating the left part and the right part, I'll have to recalculate the value of segment of I. So the value of segment of I should be equals to the value of segment of I times 2 plus 1 plus segment of I times 2 plus 2. So the value of the current segment should be the sum of the of its two childs, right? And it doesn't return anything because it's void. That's it. Again, do you have any questions in the update function? Anything is not clear here? No questions? Everything's clear?
So Ahmad, here we are following the top-down approach for the update, right?
Yes, yes.
So can we follow the bottom-top approach since we know the position at which we want to update the value of? So from that position, we can calculate the exact position of that item in the segment tree, and then we can form the bottom-up approach to update all the parents.
Um, I didn't get. So you say that it's easier to do it bottom up?
Yes.
I think no. So bottom up is much harder than top down. So if you think about it, um, so actually I never implemented a top down, a bottom up approach, but it's doable, but in much harder way. Why? Because we don't think about, we are not calculating anything, and we are not checking if I am out of bounds or not with this top-down approach. Well, I'm just checking if I am at every node, if I'm in the interval or not. If I'm in the interval, then I'll just return. If I'm out, then I'll just do nothing. That's it. So top-down is actually very, very easier. And to not waste time on bottom-up approach, I can show you uh, what bottom-up code looks like. It's it's fairly the same size, but it's much complicated.
Okay.
CX for this. Okay, here. So here for build, this is all a bottom up approach. So so he is just calling build and just making two for loops to calculate the values of its upper nodes. So you are seeing here that it's I see from my point of view that recursive functions are way easy. So it's just for me. So recursive functions are way easier to understand, and here it's just calculating the value, the indices of its upper parents and so on. But it's not so intuitive to the mind, so it's not so good. And and the update also the same thing. It's making a for loop and just updating the parents. It's not that good. Okay, so I think that the top down is better, way better.
Okay. Thank you.
Okay. Okay, let's solve. So now that we have our three functions ready, let's solve this question. So build is building the segment tree, query is getting the sum of some interval, and update is just updating the segment tree and doesn't return anything. Okay. Let's solve this question. I'm taking N and Q. And then so here I'm given three integers, the type of the query, and another two integers. Okay. So if type of query equals to 1, 1 KU. So if we are given 1, then we want to update the value at the kth position to u. Yes, update the value at the kth position to u. Then I'll just update the array and then call the update function. But first I want to make a minus minus because it's zero based indices. Yes, a minus minus. Oh, let's make this r. Okay, let's call this x and y. So x minus minus, which is the position, and then set a of x to y. Okay, after I updated this element, I want to call the update function. Then I call update, and here put the value of the first interval in the segment tree. So n minus 1, starting from 0 and updating the x position. That's it. So else, if t equals to 2, then I want to get the sum of the interval from x to y. So again, I make x minus minus, y minus minus. So I don't like writing two lines, so I'll just make x minus minus at the top here. Okay. So here I'll be printing the value of query of that interval. So I call query, and the interval we are looking at is x and y, and we'll start from 0 to n minus 1 for the segment tree, and we'll start at index 0 in the segment tree. And that's it. That should be okay, hopefully, if there are no errors. But let me check. Okay, I think everything should be okay. Let's try. There are errors. Okay, I'm missing here a parameter which is k. Okay. Yeah, I didn't call build. So after taking the values of the array, I should build segment tree. So I'm build from 0 to n minus 1, starting from 0. (14 to 11). Okay, that should be okay. But there is something that the solution wouldn't pass because of it. So we see that the values are large like the last problem, so we want to make everything long. Okay. So that's it. Okay, everything's okay here. Let's submit. Okay, accepted. Yeah, I didn't send you the code of the last problem, I think. So I'll send them now. Why is this code slower than this code? Yeah, no difference. Okay. So can you check if the code is visible to you or not? I sent it on the chat. Can anyone tell me if the code is visible to him or not? I think it won't be. Anyone tried the link?
That's not visible, Mohammed.
It's not visible? Okay, I'll send it on pastebin. And here is the link of the problem up there. So here I sent the code for the first problem, and here the second problem. And here the link is sent to the second problem. Okay, let's jump to another problem. These problems are very similar. Okay.